Hi, so in this one-shot video, I'm going to cover dual nature, which is a part of modern physics. So first we'll see what is the reduction in the syllabus, and then we'll see the different problem types that can be formed from this chapter, and then we'll see the important questions of last 3 years JEE mains. So without wasting much time, let's start the session. So now let us see the syllabus for JEE mains 2024. So first, there is a dual nature of radiation, then photoelectric effect, Hertz and Lenard's observation, then Einstein's photoelectric equation, particle nature of light, matter wave, De-Broglie's relation, and Davison-Germer experiment has been deleted this year, so you don't have to worry about this particular topic. You have to focus on these areas. And if I talk about the most important topics from where maximum amount of the questions are coming from this particular chapter, it will be from the photons, right? Photon is a very important topic from where I have seen many questions coming. And then photoelectric effect is there. And there will be a question from De-Broglie's relation. So these are the three most important topics. So let us see. So what is wave-particle duality of light? So there are some theories which believe light is a particle, and there are certain theories which believe light as a wave. So we are going to discuss some of these theories. So if you treat light as a particle, so there are two important theories. First is Newton's corpuscular theory, and second is Maxwell's Planck's quantum theory. Both these theories treat light as a particle. And there are two important theories that we have to briefly understand. First, which consider light as a wave. First is Huygen's theory, Huygen's wave theory, and second is the Maxwell's electromagnetic wave theory. So let us understand briefly about these theories. So Newton's corpuscular theory. So Newton proposes this theory in the year 1704. Now let us see some key points about this theory. First, the light is consists of little invisible particles known as corpuscles. And if there is a luminous source, it will constantly emit these particles. And when these corpuscles strike the retina of our eye, we have the sensation of the vision. And they travel with the speed of light, which is 3 into 10 raised to power 8 meters per second in vacuum. And the velocity changes as these particles move from one medium to the another medium. And different colors of the light are because of the different sizes of the corpuscles. So these are the key points about this particular theory. And there is one more important point, that is the rest mass of these particles is 0. So you have to keep these points in your mind. Now let us see what is Max Planck's quantum theory. So according to this theory, all matters, they absorb and emit energy in discrete quantities. And the smallest packet of energy is called quantum. And in case of light, it is known as photon. And the energy of quantum is proportional to the frequency. So Max Planck has given this relation that the energy of one quantum is equals to h times nu, where h is the Planck's constant. So h is equals to 6.626 into 10 raised to power minus 34 joules second. So this relation you have to remember. Okay, so we can say this is nothing but the energy of the photon. The another important theory is Huygen's wave theory. So you must have studied this theory in wave optics. So according to this theory, if there is a point source, and if we take the locus of points which are equidistant from this point source, now the locus of these point is known as a wavefront. And the different points on this wavefront will act as the secondary sources. So these are secondary sources. Now these secondary sources will generate secondary wavelets, and these secondary wavelets will travel with the speed of the wave, which is nothing but 3 into 10 raised to power 8 meters per second in vacuum. Now let us understand the propagation of energy in the form of wavefronts with an animation. So let us see. So we have a wavefront. Now these are the secondary wavelets which are being generated, and the common tangent to these secondary wavelet give us the new position of the wavefront. So this is all about Huygen's wave theory. Now let us see the key points. Whatever I have mentioned here, let us see that in writing. So first, the locus of all points, locus of all the particles vibrating in the same phase is known as a wavefront. Second point, the light travels in the medium in the form of wavefront. Third, every point on the wavefront becomes the source of secondary wavelets, and it emits secondary wavelets in all directions which travel with the speed of light. And the tangent plane to these secondary wavelets represents the new position of the wavefront. So these are the key points about Huygen's wave theory, and you have to remember this. The fourth theory is Maxwell's electromagnetic wave theory. Now, according to this theory, the source is emitted, the energy is emitted from any source continuously in the form of radiation, which is also known as a radiant energy. And we have a oscillating perpendicular electric and magnetic field, and both perpendicular to the direction of propagation of the radiation. So let us understand this. So this is the example of a plane polarized electromagnetic radiation. So can you see x-axis is the direction of propagation of electromagnetic wave, and electric field and magnetic field, they are oscillating in perpendicular planes, and they are always in phase, right? So you have to remember this. And the radiation possesses wave characteristic and travel with the speed of light. And radiations are known as electromagnetic radiation or electromagnetic waves. You must have studied this in EM waves, right? Okay, so and the last point about this theory is these waves do not require any material medium for their propagation. They can travel through vacuum. Okay, now let us come to a very important part, that is photons, right? Properties of photon, and we can expect a question from this particular section. So first of all, the photons, basically they travel with the speed of light, which is 3 into 10 raised per 8 meters per second in vacuum, and their rest mass is 0. So do remember this. And the energy of photon will be given by E equals to h nu, where nu is the frequency, h is the Planck's constant. We have already studied this in Max Planck's quantum theory. And if we want to increase the intensity, it means if I want to increase the intensity of radiation, it can be done with the increase in number of photon incident per unit area per unit time. Suppose if there is an area, and let us say 3 photons strike this area normally in 1 second. Now, if I want to double the intensity, what I can do, I can double the number of photons. Suppose if we have 6 photons, now the intensity has doubled. So do remember this, by increasing the number of photons, we can increase the intensity. Now, the fourth point, suppose, is the Einstein's relativistic energy and momentum relation. Since the rest mass is 0, if I want to find the energy of photon, we cannot use half mv square, right, that we use for particles. So here we have to use this relation, A equals to root mc square whole square plus cp square, where m is the rest mass, p is the momentum, c is the speed of light in vacuum. So if we apply this equation for photons, we know that m is 0. So E comes out to be root 0 plus cp square. So this gives us as cp. So the energy of photon is equals to c times p. So the momentum of photon will be given by E by c. Or energy can be written as h nu, and we can also write this as hc by lambda. So it is nothing but h by lambda, right? So do remember this relation, it is very important relation. So these two formulas you have to remember. Momentum will be given by E by c, and the energy will be given by h nu. Okay. Now so in this particular chapter, or in modern physics, usually the energy is measured in electron volt. Now let us see how we can convert joules into electron volt, or we can say, suppose if we have given a photon whose wavelength is given in angstrom, how we can convert that into electron volt. So if we have given wavelength in angstrom, we can find the energy in electron volt by using this relation. So let us understand. Suppose if the wavelength is given as 1000 angstrom, so the energy will be 12400 divided by 1000. So this will be 12.4 electron volt. Okay, so like this we can find the energy of a photon. Okay, right. So now next concept is the rate of photon emission from the source, right? So then how many photons are being generated per second? So it will be given by this formula, P by h nu, where P is the power. So P is power and nu is the frequency, right? And lambda is the wavelength, right? And h is the Planck's constant. So do remember this formula because I have seen the direct question from this formula in exam. Next is the intensity of a point source. If there is a point source and we want to find the intensity at a distance r from the point source, let us say the power of the point source is P, then intensity will be defined as power per unit area of the wavefront. Now the wavefront which is at a distance r will be 4 pi r square. So the intensity will be given by P upon 4 pi r square. Again, very important formula. Okay, next is the force and the radiation pressure exerted by the light beam on the surface. So we are going to consider these three cases. First is the perfectly reflecting surface. So if we have photons which are incident on a perfectly reflecting surface, then what is the force exerted by these photon on that surface? Then we'll study perfectly absorbing surface, then partially reflecting surface. Some of the photons will get absorbed, some will get reflected. So what will be the force exerted by those photons on that particular surface? Now let us see the first case, perfectly reflecting surface and for normal incidence. So if there is a surface, it's a perfectly reflecting surface. Now we have a photons which are incident normally. And let us say the area is A and I is the intensity. I is the intensity of the radiation and C is the speed of light in vacuum. Then the force exerted by these photon on this area will be given by 2IA by C. Do remember this formula. And if you want to find the radiation pressure, or the radiation pressure will be given by normal force per unit area, right? So here normal force is nothing but 2IA by C, and if you divide this with the area, we will get the radiation pressure, that is 2I by C. Okay. Now let us see the case of perfectly absorbing surface. Now let us say this surface is perfectly absorbing, and again photons are being incident normally. So we are considering normal incidence, and the area is A, intensity is I, and C is the speed of light in vacuum. So the force exerted by these photon on this area, so that force will be in the downward direction. Similarly, in this case, again, in the perfectly reflecting surface, the force is again in the downward direction. So in this case, the force will be given by IA by C. And if you want to find the radiation pressure, it will be I by C by dividing force with the area. Now let us see a case of partially reflecting surface. So we have a surface which is partially reflecting, and let us say R is the fraction of photons getting reflected, right? So if R is the fraction of photon getting reflected, then 1 minus R will be the fraction of photons getting absorbed. And we are considering normal incidence. So photons are being incident normally. And again, the intensity is I and the area of this surface is A. So in this case, the force exerted by these photon on this surface will be given by IA by C times 1 plus R, where R is the fraction of photon which are getting reflected. So I is intensity, C is speed of light in vacuum, A is the area. So this is the formula. And I have seen a direct question from this formula in one of the JEE. So, and the radiation pressure will be I by C times 1 plus R. Just divide force by the area, we will get the radiation pressure. Now let us see the oblique incidence. So if we have a perfectly reflecting surface and the photons are being incident obliquely and the angle of incidence is theta, right? So photons are coming like this. And the intensity of the photon is I. Again, C is the speed of light in vacuum and A is the area on which these photons are being incident. Now in this case, the force exerted by the photon on the surface will be in the downward direction. So this force will be given by 2IA by C cos square theta. So there is only the difference of this cos theta term. So cos square theta. So we'll multiply 2IA by C with cos square theta. And the radiation pressure will be nothing but 2I by C cos square theta. So again, remember these two formulas. Now the case of perfectly absorbing surface for oblique incidence. So there is a surface and photons are being incident like this, and the angle of incidence is theta. And these photons are getting absorbed. So if these are getting absorbed, so after collision, we can say the momentum of the photon is getting changed in this particular direction, right? So we can say it will exert force in this direction on the surface. So that is the force exerted by the photon on the surface. So the normal component of this force, Fn, right? Now this Fn will be given by this formula IA by C cos square theta. And if you want to find the radiation pressure, it will be I by C cos square theta. So do remember these two formulas as well. Okay, right. So now a very important topic, force on a perfectly absorbing body of any shape in a parallel beam of light. So it will be given by this formula, I by C times the projected area of the body. So let us see a case. Suppose we have a perfectly absorbing or a reflecting body, and photons are being incident normally, right? And let us say this sphere has a radius r. So there will be a force exerted by the photons on the sphere in the right direction, and this force will be given by, where I is the intensity, so I by C times the projected area. So what is the projected area? Suppose if the light is coming from here, if I want to form the shadow will be a circle. So it will be pi r square. So that is the projected area. So this is the force exerted by the parallel beam of light on this sphere. So even if this sphere is reflecting, perfectly reflecting, the force will remain same. If it is partially reflecting, again the force will remain same. So do remember this formula, right? Now let us see one more case. Suppose we have a cone, and this cone base radius is r and its height is h, and we have photons which are coming like this. Parallel beam of photon is coming. Now in this case, the projected area will be, you can say, it will be a triangle. So let me show you that triangle. So basically this triangle, right? So and this base of this triangle will be nothing but the diameter, and the height is nothing but h. So here the area will be half base times the height, so that is RH. So we can say the force exerted on this perfectly absorbing cone will be in the right direction, and that force will be I by C times the projected area, which is RH. So that is the answer in this particular case. So if you have another body of any shape, so what you have to take, you have to find the projected area of that body and make sure it is a perfectly absorbing body. The result, like, it is same for perfectly reflecting sphere, right? But it is not same for every case. If suppose if this cone is perfectly reflecting, in that case the force is not in the right direction. Its direction will be something else. So do remember this, right? So this is very important concept. I have seen question in JE from this particular formula. So now let us see some of the illustration on the concept that we have just studied. So we have given a parallel beam of light of wavelength 900 nanometers. So lambda is given as 900 nanometer, which is 9 into 10 raised power minus 7 meters. And the intensity is given as 100 watt per square meter. So intensity is 100 watt per square meter. Is incident on a surface perpendicular to the beam. The number of photon crossing 1 square centimeter area perpendicular to the beam in 1 second. Okay, right. So if we know intensity, so can we find the power of the source? So power is intensity times the area, right? So intensity is 100, area is 10 raised to power minus 4, right? Because 1 square centimeter is the area. So this will be 10 raised to power minus 2 watt. So that is the power. Now if you want to find the number of photons crossing this area in 1 second, so we can use this formula. So number of photons generated, right, per second. So number of photons per second will be P lambda by hc. So we can use this formula, and we know that power is 10 raised to power minus 2, lambda is 9 into 10 raised to power minus 7, and h is 6.626 into 10 raised to power minus 34, and c is 3 into 10 raised to power 8. So let us simplify this. So we have 1 upon 2.2 times 10 raised to power minus 2 minus 7 plus 34 minus 8. Now 1 by 2 is close to 0.5, right? So in the option, can you see there is a factor of 4.5? So it is nothing but 0.45 times 10 raised to power. So let us simplify this. So we have 8 plus 7 will be 15, 17. So it will be plus 17. So this will be 4.5 into 10 raised to power 16. So these are the number of photons which are crossing 1 square centimeter in 1 second. So option B is the right answer. Now let us see another illustration. It came in 2022. So just try to pause the video and solve this question on your own. Yeah, so sunlight falls normally on a surface of area 36 square centimeter and exert an average force of 7.2 into 10 raised to minus 9 Newton within a time period of 20 minutes. Considering a case of complete absorption, the energy flux of the incident light. So can you see there is a new word known as energy flux. Now what is energy flux? So if you're not aware like which physical quantity that they are talking about, just look at the options. So in the option they have mentioned watt per square centimeter. So it means it is nothing but the intensity. So we have to find intensity. Okay, now let us see how we can do that. So force is given to us and it is a completely absorbing surface. So we can say the force is nothing but the rate of change of momentum per second. So force can be written as IA by C. And we have to find the intensity, right? And the force, and we have given area. So area is given to us, force is given to us, and time period is also given to us, right? But I don't think it is required to, the time period is not required to find intensity. So force is 7.2 into 10 raised to power minus 9 and multiplied with C, which is 3 into 10 raised to power 8, divided by the area, which is 36 into 10 raised to power minus 4. Now let us simplify this. So this is 12 and this will be 0.6. So 0.6 times 10 raised to power minus 9 plus 8 plus 4. So 12 minus 9 will be 3. So it will be 600. So the intensity is 600 watt per meter square. But the options are given in centimeter square. So what we can do, we can write this as 600 divided by 10 raised to power 4. So this will become watt per centimeter square. So this is nothing but 0.06 watt per centimeter square. So can you see option D is matching with our answer. So D is the right answer. Right. So now let us see another illustration. Again, pause the video, try to solve this question on your own. It came in 2022. So we have given nearly 10% of the power of a 110 watt light bulb is converted to visible light. Now let us find the power of light energy. So it will be 10% of 110. So that will be 10 by 100 times 110. So this will be nothing but 11 watt. Now the change in the average intensity of the visible radiation at a distance of 1 meter from the bulb to a distance of 5 meter is A times 10 raised to power minus 2 watt per square meter. The value of A. So in this question, we have to find the change in intensity. Okay, as the distance is being increased, what would happen? The intensity will decrease, because we know that intensity is given by power upon 4 pi r square, right? For a point source. So when we given a light bulb, we always treat light bulb as a point source. So intensity will be P upon 4 pi r square. So the change in intensity will be what? Delta I will be, power will remain same, 4 pi will remain same. So we can say it will be 1 by 1 square minus 1 by 5 square. Now let us simplify this. So power is 11, 4 and pi we can write it as 22 by 7. And this will be 1 minus 1 by 25. So this can be written as, so it will be 2. So 7 by 8 times 24 by 25. So this will be 21 by 25. Okay, so if I multiply numerator and denominator by 4, we will get 100 in the denominator, right? So this will be 84 into 10 raised to power minus 2 watt per meter square. So that is the change in the intensity. And if we compare our answer with the question, in question it is A times 10 raised to power minus 2. So we can clearly see that A is nothing but 84. So A is 84. Got it? So that is the answer. Now let us see one more illustration. Now again, pause the video, try to solve this question on your own. Yeah, so the light is incident normally on a completely absorbing surface with the energy flux. So energy flux is nothing but the intensity. So intensity is given to us 25 watt per square centimeter, and we incident this light normally. If the surface area is 25 square centimeter, so area is given to us, that is 25 square centimeter. The momentum transferred to the surface in 40 minutes time duration. Momentum transferred in 40 minutes. So do you know what is the momentum transferred in 1 second? It is nothing but the force exerted by the photon on the surface. So force formula for perfectly absorbing surface is IA by C. That formula we have seen, right? Now intensity is given as 25 watt per square centimeter. Area is given as 25 square centimeter. So no need to convert centimeter to meter, right? Because the centimeter square will eventually get cancelled out if we take the product of intensity and the area. Divided by 3 into 10 raised to power 8. Now this is the force exerted, right, by the photons on the surface, and this is nothing but this is basically the momentum transferred by the photon in 1 second. So if this is the momentum transferred by the photon in 1 second, then the momentum transferred in 40 seconds will be this times 25 times 25 upon 3 into 10 raised to power 8 times the time, right? So time will be 40 minutes. 40 times 60, so it is in seconds. So let us simplify this. So this will be 20. So let us so 625 times 8 times 10 raised to power minus 6, right? So this comes out to be, so this will be 1250. So 2500 times 10 raised to power minus 6. So it will be 2.5. Okay, let me again check. 4, 625, 20. So 625 times 8 times 10 raised to power minus 6. Okay. And anything else that we have missed in this question? 40 minutes. Okay. Oh, sorry. So it is 5,000. Sorry. It is 5,000 times 10 raised to power minus 6. So it comes out to be 5 into 10 raised to power minus 3. And Newton second. So option C is the right answer. So I hope this concept is clear to you. It came in 2019. Now let us see one more important question. 50 watt per square meter energy density of sunlight is normally incident on a surface of solar panel. Some part of the incident energy, that is 25%, is reflected from the surface and the rest is absorbed. So we have given R, and R is 25 by 100, which is nothing but 1 by 4. The force exerted on 1 square meter surface area will be close to. So we know that in case of a partially reflecting surface, and if we have normal incidence, the force is given by IA by C times 1 plus R. Okay, so if we put the values, intensity is given as 50, area is given as 1, C is 3 into 10 raised to power 8, 1 plus 1 by 4. So this will be 50 times 5 by 4, and then there is a 3 in the denominator times 10 raised to power minus 8. Okay, so if we simplify this, so it comes out to be 125 by 6 into 10 raised to power minus 8. So this will be close to, so basically we have to find the answer closest to the option. So that will be around 20, close to 20 into 10 raised to power minus 8 Newton. So option B is the right answer. Okay, right. So now let us see the next concept. So we are done with the photons. So you have to remember the formulas that we have studied. Now let us see this concept. So De-Broglie hypothesis. So according to De-Broglie, if a light has a particle nature, so we can assign wave nature to a particle. So according to him, that the particle property, which is momentum, can be related to the wave property, that is wavelength. So he has given a formula with which we can find the wavelength associated with a particle. So the De Broglie wavelength will be given by h by p, where p is the linear momentum. So p is linear momentum, and we know that p square by 2m is nothing but the kinetic energy. So we can write p in terms of kinetic energy as root of 2mk. Okay, so we can write p as root of 2mk. Now suppose if we have a charged particle. So in case of a charged particle, say we have a positively charged particle, and if we accelerate this positive charged particle through a potential difference of say V, then the kinetic energy acquired by this positive charged particle will be the charge of this particle times the potential difference, QV. So this is nothing but the kinetic energy acquired. So we can write kinetic energy in terms of potential. So it will be K will be QV. So we can also write linear momentum as root of 2m QV. Right? So do remember this formula. And suppose if we want to find the wavelength of some of the important charged particles, say electron, proton, deuterium, alpha particle. So what we can do, if you see this H, M and Q, these are constant for that particular particle. So if we simplify that, the De-Broglie wavelength for electron will be 12.27 upon root V, where V is the accelerating potential. And so with this formula, we can find the wavelength in angstrom. For example, if in case of an electron, if V is 100, in that case, the lambda will be 12.27 divided by 10 angstrom. So it is 1.227 angstrom. So I would recommend to remember these formulas, because otherwise, if you convert these known factors in exam, it will take lots amount of time. So I would recommend do remember these formulas. So in case of proton, the factor will become 0.286. In case of deuterium, it becomes 0.0202. In case of alpha particle, it becomes 0.101. Right? So do remember these formulas. Now, sometimes they are in exam, they will ask you the De Broglie wavelength of an uncharged particle or a gas molecule. Now let us see what we can do in that case. So in case of a gas molecule, we know that in kinetic theory of gases, we have seen the average kinetic energy is given as 3/2 kBT, right? So we can replace kinetic energy with 3/2 kBT. So we can write root of 2mk with root of 2m 3/2 kBT. So this 2 will get eliminated. So we'll get root 3m kBT. So do remember this formula. Right? So I hope the concept is clear to you. Now let us see the different the important question from this particular section. Right. So this question came in the year 2021. So just pause the video and try to solve this question. Right. So a particle is traveling with 4 times as fast as an electron. Assuming the ratio of the De Broglie wavelength of the particle to that of the electron is 2:1. The mass of the particle is. So what we have given, the speed of the particle is 4 times the speed of the electron. And we have given the ratio of De Broglie wavelength of the particle to that of electron as 2:1. We need to find the relation in their masses. And we know that lambda is h upon mv. Right? So we can say, so the masses will be different, speeds are different. So we can just put the values. So we can write this as lambda p can be written as h upon mv. So we can write this as MEVE divided by mp times vp equals to 2/1. And we know that VE by VP is nothing but 1/4. So this can be written as ME upon MP times 1/4 equals to 2/1. So mass of the particle will be 1/8 of mass of electron. Right? So do remember this. So if you look at, if you compare our answer with the option given, it will be option 4. Right. So now let us see another concept, another question. It came in 2021. An electron of mass m and a photon have same energy. So there is an electron and they have the same energy. Okay, so we can say E for electron will be half m v square. And for photon, the energy is also same. The ratio of the wavelength of electron to that of photon. Okay, right. So if you want to find the wavelength for electron, it will be h upon mv. And from this relation, we can say v is nothing but root of 2e by m. where m is the mass of the electron. And okay, right. So, and the wavelength of photon will be energy, which is nothing but, okay, right. So, we know that energy is hc by lambda, right? So, lambda of photon will be hc by E. So, we can say it will be hc by E. Now, let us find the ratio. So, lambda E by lambda photon will be h by m root m upon 2e divided by hc by E. So, h will get eliminated. So, we have E by mc root m upon 2e. Now, let us take this E by m into the square root. So, we'll have 1 by c root E by 2m. So, if we compare our answer with the option 2 is the right answer. Got it? Right. So, next is the De-Broglie wavelength associated with an electron and the proton were calculated by accelerating them through a same potential of 100 volt. What should nearly be the ratio of their wavelength? Okay, right. So, let us see what is the relation of De-Broglie wavelength in terms of potential. So, we know that lambda is h upon root 2mqv, right? So, we have given an electron and a proton. So, the charge will be same, right? So, in terms of magnitude, the charge will be same. So, we can say lambda will be inversely proportional to the square root of m, right? Why? Because charge is same, potential is same. So, only the thing which is changing for electron and proton is mass. So, we can say lambda is inversely proportional to square root of mass. So, we can say, so the ratio of their wavelength, so lambda of electron to lambda of proton will be root of mass of proton upon root of mass of electron. And we know that mass of proton is approximately 1860 times the mass of electron. So, we can write this as root of 1860. And root of 1860 is quite close to 1860 is quite close to the square of 43. So 43 square root of that. So that will be 43. So option 4 is the right answer. Okay. So again, pause the video to try to solve this question. So, okay. So an electron, a doubly ionized helium ion and a proton are having same kinetic energy. So here they are saying same kinetic energy. The relation between their respective De-Broglie wavelength. Okay. So we have to compare the wavelength of these charged particles. So lambda in terms of kinetic energy can be written as h upon root 2mk. Since we have different charged particle, their masses will be different. So we can say lambda is inversely proportional to square root of mk. And kinetic energy is also same, right? So we can also remove kinetic energy from the proportionality. So we can say the lambda is inversely proportional to square root of mass. Now basically we have to check the value of 1 by root m to compare the wavelengths. So 1 by, so in the option, okay, right. So 1 by root m. So we have electron, mass of electron. Then we have helium 2 plus. For helium 2 plus, what is the mass? It is, you can say it will be 4 times the mass of proton. And then for proton, it is 1 upon root mp. Smaller the mass, greater the lambda, right? So we can say the lambda of electron will be greatest, and it will be greater than the lambda of proton, and the smallest wavelength will be of alpha particle. So that will be lambda He double plus. So if we compare our result with the option, so option C is the right answer, right? Lambda A is greater than lambda P, and lambda P is greater than lambda He2 plus. I hope this question is clear to you. Now let us see another question. The De-Broglie wavelength of an electron having kinetic energy E is lambda. So we have given kinetic energy E, wavelength is lambda. The kinetic energy of the electron becomes E by 4. Then its De-Broglie wavelength will become, okay. So we have lambda is 1 upon root 2 me, where E is the kinetic energy. Now, if the kinetic energy is decreased by 4, what would happen to the lambda? So you can clearly see that if E is decreased by 4, the lambda will increase by 2. So the wavelength will become 2 lambda. So option 3 is the right answer. Okay, right. Now let us see this question. It came in 2022. A proton, a neutron, an electron, and an alpha particle having same energy. And lambda p, lambda n, lambda e, lambda alpha are the de Broglie wavelengths of proton, neutron, electron, and alpha particle. Then choose the correct relation. So again, we have to compare wavelengths of these charged particles. And they have same energy. If energy is same, we can say lambda will be inversely proportional to the mass. Right? So for proton, then we have neutron and electron, and then we have alpha. Smaller the mass, greater the lambda. And we want to write down in terms of, let us say, let's find this in terms of increasing order, right? So it will be 1 upon root mp, and this will be 1 upon root mn, where mn is the mass of one neutron, and this will be 1 upon root me, and this will be 1 upon root 4 mp. Can you see, we know that the mass of neutron is greater than mass of proton. So lambda of neutron will be less than lambda of proton. And we know the mass of electron is smallest, so its lambda will be greatest. So lambda of electron will be greatest, right? So we can say it's lambda E, and the lambda for alpha will be less than the lambda of proton. Can you see? Because the mass of alpha is greater. So lambda of alpha will be less than the lambda of proton. So lambda of alpha will be less than lambda of proton. Okay, right? So if we write down this in increasing order, and we can also say lambda of alpha will be less than the lambda of neutron. So lambda of alpha is less than lambda of neutron, and it is less than lambda, and lambda of neutron is less than lambda of proton, and it is less than lambda of electron. So if you look at the option B is the right answer. I hope the concept is clear how to compare the de Broglie's wavelength. Okay, now let us see this question. It came in 2022. An electron with a speed v and photon with a speed c have the same de Broglie wavelength. So lambda of electron is same as lambda of photon. If the kinetic energy and the momentum of electron are E, E, and PE, and that of the photons are EPH and PPH respectively, which of the following is correct? So basically we have to find the ratio of energy and the ratio of momentum. So let us see. Lambda is same, right? So we know that energy of photon can be written as hc by lambda of photon, right? And lambda of electron can be written as h upon mv. And the lambdas are same, so we can say lambda p, which is hc by ep, it is same as h by mv. Now from this we can say hc by ep is equals to same as h by mv, so h will get eliminated. So we have a relation, so we have ep, right? Energy of photon will be equals to mcv. Now energy of electron is half mv square. Now if you find the ratio, so E divided by EP, that will be half mv square upon mcv. So m will get eliminated, 1v will get eliminated, so this will be v by 2c. Can you see? Option B is the right answer. So since it's a single option correct, so we no need to have to check for the other quantities, other options. So option 2 is the right answer. Right, so now let us see this question. Again, it came in 2022. So can you see this is very important topic, de Broglie's wavelength, because you can expect a question from this topic in your exam. So de Broglie is a wavelength for an electron and the photon is lambda E and lambda P. And for the same kinetic energy of the electron and photon, which of the following represents the correct relation between the de Broglie wavelength of the two. Right, so they have same kinetic energy. So we can say, yeah, for same kinetic energy. So we can, so the energy of photon will be hc by lambda of photon, and energy of electron will be half m v square, or we can also write this as p square by 2m, and p can be written as root of 2mk. This is the momentum of electron. So if you want to find the wavelength of electron, it will be h upon root it will be h upon root 2mk, and k is nothing but E, right? So that is the wavelength. And we have to find the relation between the wavelength of photon and the electron. So lambda of photon is inversely proportional to energy. So we can say lambda E will be inversely proportional to root of E, and this is proportional to, and E is inversely proportional to lambda P, right? So root E will be inversely proportional to root lambda P. So this will be directly proportional to root of lambda P. So we can say lambda E square on both sides. So lambda E square will be directly proportional to lambda P. So option A is the right answer. Right, so now let us see one more case. So again, pause the video, try to solve this question on your own. Right, so the electron of mass m with initial velocity v, which is v naught I cap, where v naught is positive, is moving in the electric field which is in the negative x direction because E naught is positive. If at t equals to 0, de Broglie wavelength is lambda naught, which is h by mv naught, then its de Broglie wavelength after time t is given by. Right, so what we have given, this is the x-axis, and there is an electron which is moving in the positive x direction with a velocity v naught. And there is an electric field which is in the negative x direction. So if the electric field is in the negative x direction, the force exerted on the electron will be in the positive x direction. So if the acceleration and velocity are in the same direction, we can say the electron will accelerate, its speed will increase. So if speed is increasing, the de Broglie wavelength will decrease. Okay, now its de Broglie wavelength after time t, since we have a constant acceleration, and acceleration will be given by E times E naught divided by m, where E times E naught is the force experienced by the electron and m is the mass of the electron. So we can apply equation of motion in that you've studied in kinematics. So it will be velocity after time t will be initial velocity, which is v naught, plus E capital E naught by m times t, right? So this is the speed. So the new wavelength, let us say it is lambda prime, it will be h upon m v naught, and I can also write v naught as common, 1 plus E naught t upon mv. So it will be m v naught times 1 plus E capital E naught t upon mv naught, right? Okay, and this factor h by mv naught is nothing but the original wavelength, which is lambda naught. So this is nothing but lambda naught. So the answer will be lambda naught upon 1 plus E naught t upon mv naught. So let us compare this answer with the option. So lambda naught upon 1 plus E. So option D is the right answer. Okay, now let us see this case. Again, pause the video, try to solve this question. An electron accelerated through a potential difference V1 has a de Broglie wavelength of lambda. When the potential is changed to V2, its de Broglie wavelength increases by 50%. The value of V1 and V2 is equals to. So we know what is the relation of de Broglie wavelength in terms of potential difference. It will be 1 h upon root 2m q v. Since the charged particle is same, so we are talking about the electron. So q is constant, mass is constant, h is constant. So we can say lambda is inversely proportional to square root of potential difference. So from here we can say lambda 2 by lambda 1 will be square root of v1 by v2. So, and we have given that the lambda has increased by 50% because the potential has, obviously the potential will decrease, right? If the potential is decreasing, the lambda will increase. So lambda 2 is 50% more than lambda 1. So we can say it will be 1.5 times lambda 1. So lambda 2 by lambda 1 is 1.5. So it is 1.5. If I square this, we will get the ratio of V1 and V2. So this will be 9 by 4. So option 2 is the right answer. Right, now let us see another question. It came in 2021. A particle of mass 4m at rest disintegrates into two particles of mass m and 3m. So in collision chapter or conservation of momentum, you must have studied if we have a single mass, it splits up into two particles. In that case, these particles will move in the opposite direction to conserve the momentum. So initial momentum is 0. So momentum after collision has to be 0. So if we have a particle of mass 4m, if this particle splits up into two parts, let us say this is 3m and this is m. It will move in this direction, it will move in this direction, and both will be having same momentum in magnitude. Okay, if this is p, this is also p in magnitude. So the ratio of the De-Broglie wavelength, and we know that lambda is h by p. If momentum is same for both the particle, their De-Broglie wavelength will be same. So option 4 is the right answer. Okay, now let us see this question. A particle of mass 9.1 into 10 raised to power minus 31 kilogram travels in medium with a speed of 10 raised to power 6 meters per second, and a photon of a radiation of linear momentum 10 raised to power minus 27 kilogram meters per second travels in vacuum. The wavelength of the photon is dash times the wavelength of the particle. So try to pause the video and solve this question. Okay, right. So we have to find lambda of proton. Let us say the lambda of proton, sorry, not proton, lambda of photon is x times the lambda of particle. So we have to find what is this x. And the lambda of photon, we know that energy is hc by lambda of photon, right? So it can be written as hc by E. And the lambda of the particle, we know that lambda of particle will be h by the momentum, right? Mass times the velocity. So this will be h upon mv. So let us put the values. So x is mvc divided by E, right? And we have given a photon of a radiation of linear momentum. So we know that in case of a photon, the momentum of photon will be given by E by C, right? So E can be written as momentum of photon times C. So this can be written as mvc divided by momentum of photon times C. So this C will get cancelled out. So it will be m 9.1 into 10 raised to power minus 31. Speed is given as 10 raised to power 6 for the particle. And the momentum of photon is given as 10 raised to power minus 27. So this will be 9.1 times 10 raised to power minus 4 plus 2. So this comes out to be 910. So this x is nothing but 910. So that is the answer. Right, so we are done with photons. The next topic that we're going to start is photoelectric effect. So in photoelectric effect, let us see what we're going to study. So first we'll see the observation of Hertz and Lenard and Hallwach. Then we'll see the important terms related to this effect, that is the work function, threshold frequency, and threshold wavelength. Then we'll see the experimental setup. Suppose if I want to observe this effect in a lab, so what should be the experimental setup for that? Then the Einstein's photoelectric effect equation. And then we'll see how the current or the photo current varies with the potential difference and what is the concept of saturation current and stopping potential. Then we'll see the graph of saturation current with the intensity and then the graph of stopping potential with the frequency. So let us see what is a photoelectric effect. Suppose we have a metal surface and we know that in metals we have free charge carriers which are roaming freely inside the lattice. So suppose if we incident photons of sufficient minimum frequency. So if that photon is being absorbed by those freely moving electron, loosely bound electrons, so there is a possibility that that electron will come out of the metal surface. And this phenomena of ejection of electron from the metal surface is known as photoelectric emission. And the electrons which are coming out are known as photoelectrons. Now let us see how this effect was discovered in past. So first let us see what is the Hertz observation. So Hertz, like we all know Hertz, he was responsible for generation of electromagnetic radiation in lab and also receiving those electromagnetic radiation wirelessly. So Hertz was doing his experiment. So he was generating electromagnetic wave and receiving electromagnetic waves at the receiver end. So at the receiver, how do we know that we have received some signal? So there is a spark between these two electrodes because there will be some EMF induced in this receiver. If there is an EMF induced, there will be a strong electric field in this region, right? There is a strong electric field. And due to that strong electric field, there will be some, you can say, dielectric breakdown of the medium. So there will be charge carriers created in this region. And due to that, there will be a spark. So by accident, Hertz observed that if we incident ultraviolet light on the receiver, the spark has enhanced. So basically it becomes bigger, right? So that was the first observation of Hertz. So Hertz published about this observation in a research paper, and then based on this observation, Lenard and Hallwach carried out some experiments. So now let us see what Lenard has done. So Lenard has taken a metallic plate, which is known as an emitter plate. This is a emitter plate, and this is the collector plate. And he has placed these two plates in an evacuated glass tube, right? Evacuated glass tube. And then he incident UV rays on this emitter plate. And he observed that there is some current in the circuit, right? It means some charged particle has come out of the emitter surface and they move from the emitter to the collector plate and constitute the current. So that is the observation of Lenard. And then Hallwach further do more experimentation, and Hallwach used a negatively charged zinc material. So if we incident say UV rays, so he incident UV rays on this negatively charged zinc plate, and he found that this negatively charged zinc plate after some time becomes neutral, right? And if it keeps on adding photons, or if it keeps on bombarding this with photons, eventually it becomes positively charged, right? So from these observations, we come across this phenomena. And at that point of time, they were not aware what type of particles are coming out. So later, J.J. Thomson discovered electrons, and then it was like they came to know like these particles are electrons which are coming out. So as electrons are coming out, the material will become more positive, right? It becomes more positively charged. So I hope these observations are clear to you. You have to just have some brief idea about these observations, because there can be some theoretical question on Lenard and Hallwach's observation. Right, so now let us see the terms related to photoelectric effect. So first we'll see the work function, then we'll see the threshold frequency, and then threshold wavelength. Now let us study these terms one by one. Now work function. So work function basically is the minimum energy required to remove the most loosely bound electron from the metal surface. So it is denoted with phi, right? And we should also remember that if we want to eject more electrons, we have to incident more photons. So if we talk about increasing number of photons, it means we have to increase the intensity. So do remember this. So the energy of photon incident on metal will not necessarily cause emission of the electron, even if its energy is more than work function. So what does it mean? Suppose we have sufficient energy, photon has sufficient energy, but suppose if that photon is being absorbed by an electron which is not loosely bonded, in that case, we'll not able to remove that particular electron. Okay, so do remember this. So that's why the number of ejected photoelectrons is always less than the number of incident photons of sufficient energy. But if nothing is given in the question, you can assume that the number of photons incident is same as the number of photoelectrons ejected. Okay, right. So the threshold wavelength is again the minimum frequency required to carry out the photoelectric emission. And we can say threshold wavelength is nothing but the work function divided by the Planck's constant. So we should remember this. For example, if we have given, say, the threshold frequency, say it is 3 into 10 raised to power 12 Hertz, right? And we want to find the work function in electron volt. So let us find the wavelength corresponding to this frequency. So it will be 3 into 10 raised to power 8 divided by 3 into 10 raised to power 12. So it comes out to be 10 raised to power minus 4. Right? So this will be in meters, right? So if I convert this into angstrom, so this will be 10 raised per 6 angstrom. So the energy, or you can say the work function in electron volt, will be 12400 divided by 10 raised per 6 angstrom. So this comes out to be 124 into 10 raised per minus 4 electron volt. So like this we can calculate the work function. Now the threshold wavelength is, you can say, the maximum. It is the minimum wavelength that is required to carry out the photoelectric emission. Threshold frequency is the minimum frequency required to carry out the photoelectric emission, and we can find the threshold frequency if work function is given to us. So it is phi upon h. So we have to remember this formula. Now the threshold wavelength, you can say it is the maximum wavelength that is required to carry out the photoelectric emission. So it is the, you can say the wavelength corresponds to the threshold frequency is nothing but the threshold wavelength. So we can also call it a cutoff wavelength. So cutoff wavelength, and for a given metal surface, threshold wavelength is the longest wavelength at which the photoelectric emission is possible. Right. So if we decrease the wavelength, then the frequency will increase. So we can say if we have a wavelength which is less than threshold wavelength, in that case the photoelectric emission will happen, right? Okay, so we can find threshold wavelength by this formula, where Hc is, or you can say the threshold wavelength is equals to Hc upon phi. Okay. Now let us understand the experimental setup that is used to study photoelectric effect. So let us go through this animation. So this is the setup for photoelectric effect. So we have a emitter plate, this is the collector plate, and these two plates are kept in a evacuated glass tube. What is a evacuated glass tube? Which does not have any pressure, so it is nearly vacuum. Now we have a source and we can alter the intensity. So how we can alter the intensity? By changing the number, or by increasing. If we increase the intensity, means we can increase the number of photons which are being incident on the emitter plate. So let us have some intensity, right? So I am keeping intensity as 50%. Now this is the intensity. So can you see, but there are no photoelectrons which are coming out. Why they are not coming out? Because the frequency is not sufficient enough. So at present we have 612 nanometer of wavelength. So if we decrease wavelength and increase intensity, electron can come out, right? So let us say, so if we decrease wavelength and increase frequency, there will be a particular wavelength at which the electrons are coming out. Can you see? And when these electrons reaches the collector plate, they constitute a current, and this current is shown here as 0.019. Okay, right. Now what would happen if I double the intensity? If I make the intensity 100, at present it is 50% and the current is 0.019. So if I double the intensity by making it at 100, so can you see the current has also become double? So it becomes 0.039. Earlier it was 0.019. So it is all, the current will almost get doubled, right? So now look at the speed of the fastest electron. So just observe the speed of the fastest electron which is coming out. So if I increase the wavelength, increase the frequency of the radiation for the same intensity, let us say we have increased. Now can you see the speed of the fastest electron has also increased? So we can say the most loosely bound electron, its kinetic energy will increase as we increase the energy of incident photon. So these concepts you have to remember. I think now we have enough knowledge, and now we can discuss the important graphs for photoelectric emission. So if you are clear about the working of photoelectric effect, now let us see a very important equation, which is Einstein's photoelectric equation. So according to this equation, and this equation is valid for most loosely bound electron. Suppose if we have a metal surface, and let us say this is the most loosely bound electron, and if we incident photon of energy, say h nu, a part of the energy of this photoelectron will overcome the work function, and the remaining energy will increase the kinetic energy of the loosely bound electron. So it will come out. So this electron will come out with certain energy. Let's say the energy is kmax, right? And the work function of this metal is phi. So we can say h nu is sum of the work function and the maximum kinetic energy. So the maximum speed of the photoelectron will be will be V max. So from this equation, we can find the desired physical quantity. Okay, right. So as we have seen that K max is nothing but h nu minus phi, where h nu is the energy of the incident photon, phi is the work function, K max is the maximum kinetic energy. So if I plot the graph of K max and the frequency, so in this equation, phi is constant, h is constant. So we can say it is of the form of y is equals to mx minus c, where the y-intercept is negative and the slope is nothing but h. So if we plot this, let us say we have two metals, so metal 1 and metal 2. So if this angle is theta and this angle is theta, so we can say tan theta is nothing but h, and the y-intercept is nothing but the work function for that particular metal. So this will be 0 comma minus phi 1 and this will be 0 comma minus phi 2. So if you plot kinetic energy versus frequency graph for any metal, all graphs will come out to be parallel to each other because they will be having same slope. So do remember this graph. Now let us see a very important term, the saturation current and the stopping potential. So let us understand that. So suppose we are plotting a graph of the photocurrent. On the y-axis we have photocurrent. This I is photocurrent, and on the x-axis we have the potential. Now what is the potential? For example, this is our emitter plate and this is the collector plate. Let me call it C and this as E, right? And we incident photons on this emitter plate. Now what would happen? The electron will come out. And let us say we have a battery whose polarity is like this, and the collector plate is positively charged. You can say collector plate is at high potential and the emitter plate is at low potential. Now due to this potential difference between the emitter plate and the collector plate, there will be an electric field. The electric field is in the left direction. Now this electric field will exert force on the photoelectrons in the opposite direction. So as the photoelectrons come out of the emitter plate, there will be a force in the right direction, and these photoelectrons will accelerate in the right direction, and then they will get collected by the collector plate. Suppose let us increase the value of this V. So if we increase the value of V, what would happen? Suppose if there were 100 photons initially which were ejected, and out of these 100 photons, let us say 50 photons are able to reach the collector plate. Okay, but if we increase V, the field will increase. So as we increase the field, more photoelectrons will be able to reach the collector plate. So as more electron reaches the collector plate, the current or photocurrent will be more. So can you see, for a given intensity, as for zero potential, if there is no potential, still there will be some electrons which are reaching the collector plate and constitute the current. But as we increase the potential, the number of photoelectrons which are hitting collector plate will increase, and there will be you can say there will be a potential difference at which whatever electrons which are being ejected are reaching the collector plate. Now this current is known as, so this value, right? This current is known as the saturation current. So we can say saturation current is a current when all ejected photoelectrons are reaching the collector plate and constitute the current. Similarly, if we increase the intensity, then the number of photoelectrons which are being ejected will increase. So can you see the graph for I2, where I2 is the intensity, I2 is greater than I1. So in this case, the graph, you can say the value of the current is more. And it is quite obvious because more photoelectrons are reaching the collector plate. And in this case, the saturation current will also increase. So we can see the saturation current depends upon the intensity. So do remember this graph. Now, what is the stopping potential? So we can say it is the minimum retarding potential required to make sure even the most energetic photoelectron is not able to reach the collector plate. So let us see. Suppose if we make the emitter plate at at high potential, right? Make it as positive, and the collector plate as negative. Something like this. Now what would happen? So there will be a field in the right direction. Now this electric field will exert force on these photoelectrons in the opposite direction. So this is the direction of force. Now suppose we have the most energetic electron. So this is a at high potential and this plate is at low potential. And we have a photoelectron, and let us say its speed is maximum, right? And its kinetic energy is kmax. Now this electron will experience a force in the opposite direction. It is going in the right direction, but it will experience a force in the left direction. And suppose before reaching the collector plate, its velocity becomes 0. So can you see there is a decrease in potential, there is a decrease in kinetic energy. And that kinetic energy has gone in increasing the electrostatic potential energy. So we can say this K max is nothing but E times the potential difference. So let us the potential difference is V naught. So the maximum kinetic energy of the most loosely bound electron will be E times V naught. So we can write it like this. So if I show this in the graph, let us consider for I1, right? I2 is greater than I1. These are the intensities. So we have seen up to this particular mark when the potential is 0. Suppose now we have a reverse voltage, right? So as we have more reverse voltage, the field will become more in the reverse direction and it will decelerate electron even more. And there will be a potential at which the photocurrent becomes 0 because even the most energetic electron is not able to reach the collector plate. So here the you can say the current will become 0. And can you see one more thing? For a given metal and for the same frequency, right? For the same incident frequency, the stopping potential is same. So let me show you. So we have h nu is equals to phi plus k max, and this k max can be written as E times V naught. So can you see if the frequency is same, work function is same for a given metal, h is also constant, E is also constant, the stopping potential will not change. So we can say stopping potential does not depend, stopping potential does not depend upon intensity. It will remain same for the same frequency. But as we change the frequency, the stopping potential will change. So this is for same. So it is clearly mentioned here for same frequency. So do remember this graph, right? How to compare if we have different intensities. Okay, right. So now let us see the graph of stopping potential with the frequency. And we have just seen this formula, right? So V naught is equals to h by E nu minus phi by E. So if I take this angle as theta and this angle is again theta. So this is metal B and this is metal A. And this is nothing but the slope, right? So this is slope and this is nothing but the y-intercept. So these are the values, right? So it's a linear graph because it is of the form of y is equals to mx minus c, where m is the slopes and c is the y-intercept. So I hope this graph is also clear to you. And suppose if I want to find the threshold, if this graph is given to us and we want to find the threshold frequency, it will be given by the x-intercept of this graph. So these are the threshold frequencies. So for metal, for different metals, the threshold frequency will be different, right? Because the work function is different for different metals. Right. So now let us see some illustration. So whatever formulas that we have seen in photoelectric effect, we are going to apply those formulas here. A metallic surface is illuminated with a radiation of wavelength lambda and the stopping potential is V naught. And if the same surface is illuminated with a radiation of wavelength 2 lambda, the stopping potential becomes V naught by 4. So we know the formula, the Einstein's photoelectric equation, it states that h nu is equals to phi plus k max. And we can also write this equation as hc by lambda equals to work function plus E times V naught, right? So that is the first equation for the first case, right? And if we increase the wavelength, so we'll become hc by 2 lambda, work function will not change for the same metal, and it will become E times V naught by 4. Now this is our second equation. And we need to find the threshold wavelength for this metal. So what is threshold wavelength? Threshold wavelength is hc by lambda naught. So this is work function, and from this we can find the threshold wavelength. Okay, right. So what we can do, we can eliminate V naught. So I can multiply the second equation by 4 So this will get eliminated. So if we subtract first from the second, we will get, so this is again 2, right? So we'll be having hc by lambda is equals to 3 phi. And phi can be written as hc by lambda naught. So we can clearly see that this hc will get cancelled out and lambda naught is nothing but 3 times lambda. Right? So option 4 is the right answer. Okay, right. So again pause the video and try to do this question. Right. So we have given two stream of photons possessing energy is equals to twice and 10 times the work function. Okay, right. So we have two stream of photon. That is the E1 is the energy of first stream, and this is nothing but 2 times the work function. And the second stream of photons has the energy 10 times the work function. Are incident on the metal surface successively. The value of the ratio of maximum velocities of the photoelectrons ejected in the two respective cases is x ratio 3. The value of x is, okay, right. So again let us plug in these values in the photoelectric equation. So we have for the first series of photons, we have 2 phi equals to work function plus maximum velocity. So I can write this as half m v1 square, right? So we can say phi is equals to half m v1 square. This is the first equation. Now for the second stream of photons, I can write 10 phi is equals to phi plus half m v2 square. That is the, or you can say 9 phi is equals to half m v2 square. So this is the second equation. Now we can divide these two equations. So the value of ratio of maximum velocity is, okay, right? So we have to find the ratio of the velocities. So we have phi upon 9 phi is equals to half m v1 square upon half m v2 square. So this m by 2 will get cancelled out, phi will get cancelled out. So v1 by v2 will be square root of 1 by 9. So that will be 1 by 3. So it is nothing but x by 3. So we can say x is nothing but 1, right? So 1 is the right answer. Okay, now let us see a graphical question. So we have given variation of stopping potential as a function of frequency of the incident light for a metal as shown in the figure. The work function of the surface is, okay, so we have to find the work function, right? And can you see the x-intercept of this graph will give us what? So we know that v naught is equals to, and we have frequency, right? H nu by E minus phi by E, right? So if we can say if this v is 0, if v naught is 0, right? In that case, H nu by E is nothing but phi by E, or we can say this nu is nothing but threshold frequency. And that what we have to, and we have to calculate the work function. So threshold frequency is given to us, that will be 5 into 10 raised to power 14 hertz. Can you see? We have given a multiplier that is 10 raised to power 14 hertz. So this is the threshold frequency. If I multiply this with h, so 6.626 into 10 raised to power minus 34 times 5 into 10 raised to power 14. Now this is in joules, right? So if I convert joules into electron volt, we have to divide by 1.6 into 10 raised to power minus 19. Okay, so if I simplify this, so 6.626 times 5 divided by 1.6. So we're getting something 2.04, right? If I simplify this, I'm getting 2.07 electron volt. So option 3 is the right answer. Okay, right. So now let us see next question. So in electric field, the electric field at a point associated with the light wave is given by this, where we can see two frequencies, right? One is 6 into 10 raised to 15, other is 9 into 10 raised to 15. These are in angular frequencies. And we have given value of H as 4.14 into 10 raised to minus 15 electron volt second. If this light falls on a metal surface having a work function of 2.5 electron volt, the maximum kinetic energy of the photoelectron. Right, so we want to find the maximum kinetic energy, and we know that the energy of the photon is equals to work function time plus sum of the work function and the maximum kinetic energy. So if I want to maximize kinetic energy, we have to maximize the energy, and we can maximize energy by increasing the frequency. So we have to take this frequency 9 into 10 raised to 15 to have the maximum value of the kinetic energy. Okay. So now let us, so we have omega, so that is 9 into 10 raised to 15. So from this we can find the frequency. It will be omega by 2 pi. So it will be 9 upon 2 pi times 10 raised to 15. And in the question we have given value of H in terms of electron volt second. So HF, that is the energy of the photon, will be 4.14 into 10 raised to power minus 15 times 9 upon 2 pi into 10 raised to power 15. So this will get cancelled out. So this will be 4.14 into 9 upon 2 pi. Okay. So can you see the numerator is close to 36 and denominator is close to 6, around 6, right? So let us see. So if you substitute the values here, so it will be 4.14 into 9 upon 2 pi, and work function is given as 2.5 plus k max. So let me calculate the actual value. 4.14 times 9 divided by 2 divided by pi, so it comes out to be 5.9 minus 2.5, that will be k max. So this comes out to be 3.4 electron volt. So that is the answer. So 3.4, so 3.42. So option 4 is the right answer. Okay, right. So now let us see the next illustration. The threshold wavelength for the photoelectric emission from a material of 5500 angstrom. So basically threshold wavelength is given, that is 5500 angstrom. So from here we can find the work function. So work function in electron volt can be given by 12400 divided by 5500. So this will be 124 divided by 55. So exact value will be around 2.25. So this is 2.25 electron volt, right? And so we incident on this material, it is illuminated with the monochromatic radiation from infrared lamps and ultraviolet lamps. So we have to find in which case there will be photoelectric emission, right? Okay. So the threshold wavelength is 5500 angstrom. If I draw the spectrum, here we have violet, here we have red, right? So this spectrum ranges from 3000 angstrom to 7000 angstrom. And the threshold wavelength is somewhere here, 5500 angstrom. So if you decrease the wavelength, in that case we'll be able to carry out photoelectric emission because the frequency will increase. So if we use ultraviolet lamp, in that case we'll be able to carry out photoelectric emission. So option C and option D, so C and D, so option 4 is the right answer. It doesn't matter what is the power, even how low the intensity is, we'll be able to carry out photoelectric emission. Now let us see another illustration. So let K1 and K2 be the maximum kinetic energies of photoelectrons emitted when two monochromatic beam of wavelength lambda 1 and lambda 2 respectively are incident on the metallic surface. And we have given a relation between lambda 1 and lambda 2. So we have to compare the kinetic energy of the ejected photoelectrons. Okay, so what we can do, we can apply Einstein's photoelectric equation here 2 times. So first for the photons of wavelength lambda 1, so we can say Hc by lambda 1 is equals to phi plus k1, and for the second second case it will be Hc by lambda 2 equals to phi plus k2. And we have given lambda 2 is lambda 1 is 3 times lambda 2. So we can write Hc upon 3 times lambda 2 equals to phi plus k1. Okay, right. So now let us multiply this equation with 3 so that we can eliminate 3. And let us, this is first equation and this is second equation. Now let us subtract these. So we have 0 on the left hand side and we have minus 2 phi and then we have plus K2 minus 3K1. So we can say K2 is equals to 3K1 plus 25. And we know that work function is a positive quantity. So K2 will be greater than 3 times K1. Or we can say K1 will be less than 1/3 of K2. So option B is the right answer. I'm pretty sure you'll also like Prague-based unique approach to guide student for their last mile journey. So if you are a student who has been preparing for JEE or NEET and you are going to write your exam in 2024, then Prague is the best platform to further refine your preparation. Other crash courses which cover 100% of the syllabus in less than 2 to 3 months, and that syllabus you took around 2 years to prepare, or more than 2 years. So it is very difficult for students to absorb 100% of the syllabus in that short amount of time. So at Prague we follow a unique approach to cater this problem. So at Prague we have a 3-step process. In step 1, a senior faculty will sit with you. He will assess your weak areas and he will guide you what are different consistent topics that you have to prepare to ace in your exam. And he will prepare a concrete plan and he will allocate the number of classes required for that. So once that plan is prepared, now we'll move to the second process, and that will be one-on-one online classes. So in one-on-one online classes, the faculty will be aligned with you, and that faculty will guide you how to apply those concepts in which you are not good at and how to solve a problem effectively. So then we move to the third process or third step. In this step, we'll align you in a test series, so where you can see where you are currently standing and how these classes are helping you out. So you can have a full syllabus test, or you can also give part test for a chapter test. So by using this approach, Ashish Mishra was able to maximize his score in JEE Mains and JEE Advanced. And at present, he is studying mechanical engineering from IIT Madras. So if you want to maximize your score in this last mile journey, so I have given a link in the description box. So you can click on that link and book a session with us. So one of my teammates will get in touch with you and he will guide you.